Welcome to the next episode of Cash It. I am Khawaja Shams, co-founder and CEO at Momento, and joining me today is Hari.
Hi everyone, I'm Harkrishn. I'm a software engineer at AWS. I'm also a project maintainer for Valkey. I've been with this project since the incubation of the project.
Awesome. How long have you been at Amazon and on the Elasticache team?
So it's more than 6 years now working for Amazon. I've been with the same team since the start of my joining. Worked on the platform team for the first few years and then moved on to the engine side of things.
The reason why I'm super excited to have you here is you wrote a sensational blog around Valkey's ability to handle 1 billion RPS. That's billion with a B. And that's a number that most of us only kind of dream about. So I'm curious, what does it take? Why is 1 billion RPS hard?
Sure. Yeah, I was not expecting it to be a bit sensational, but I knew there will be some buzz. Historically, Valkey started off with a standalone approach where there is only one primary and there are multiple replicas to it, and that doesn't scale writes, right? So there was a cluster mode introduced, and that helped horizontally scaling writes. But it was not ever intended to scale beyond, let's say, 50, 100 nodes. But slowly, as the adoption grew and customers and users wanted more number of shards in a single cluster, the the number which people had reached to were around 500 nodes in a cluster, and at that point, things were breaking pretty much in different pieces. The goal which we took was we want to see how extreme we can push the cluster and see what are the bottlenecks. And as part of that process, we also wanted to discover like the design and all of the intricacies behind it, right? So we saw there were a bunch of challenges around failover, message gossiping. There are a lot of pieces which makes the clustering system work. And the idea of reaching 1 billion RPS was still like a distant dream. And we tried to go about one piece at a time and discovering the limitation, trying to see what can be fixed, and then reaching to this milestone of 1 billion RPS. Of course, I have to mention that 1 million RPS for a single node work helped drive that effort, but clustering shouldn't become a huge bottleneck or overhead. And that was the case. And Valky as a project since 7.2 has made major improvements across different pieces to make that happen in 9.0.
The title of the blog is all about 1 billion RPS, but my takeaway was the ability to handle a cluster of 2,000 nodes that are working together with each other. Is that about right?
Yes, that's correct. Like I also was more interested on the 2000 nodes in a cluster. How does that work? But that might not sound interesting. But I've seen use cases where people want to run large clusters, running 2000 nodes in a single cluster. If people want that, so be it, and we can support it, right? If I can go bit by bit a bit into what were the key bottlenecks, I can talk about it a bit. So first of all, there's something called PubSub, which uses cluster bus for like basically there's a mess in the clustering system which is used for passing information between cross-node communication, like if someone is healthy or not, what is my current topology. So that piece of infrastructure is used for PubSub as well for supporting PubSub traffic. Like you can subscribe on any node and it can be received on any other node. That
Mhm.
was kind of the system which was built with clustering, but PubSub didn't scale well because you are broadcasting the same information across all the nodes. This is something which I fixed in version 7, where we introduced something called sharded PubSub. Basically, you reduce the traffic to one particular shard and not broadcast it to all. And then we introduce something called a lightweight message where you don't use the heavy payload to pass on the message across the cluster, rather use a very lightweight packet. So a user can run now scale basically PubSub traffic across the cluster using this sharding approach. Failover was one of the other bottlenecks. You want, if a primary goes down, that a replica takes over the primary ship of that shard and you still continue serving writes. And the observation was when there are multiple primaries failing in a shard, for example, a cloud scenario where there is a AZ, and if a AZ goes down, you don't want the cluster to be entirely disrupted. You want to rely on the high availability aspect of using multi-AZ. And Valkey was not able to handle that. And one of the community member, Bin, he helped figure out that there was a lot of conflicts in terms of who becomes a candidate and who wins the election for a given shard. So in order to tackle that, he introduced adding some delays in this operation so that there is no contention, and that helped scale the failover operation.
My takeaway then is running a 2000 shard cluster is very hard. And there were meaningful improvements that were made on the Valkey side on improving how lightweight the message bus is for the cluster bus, the speed with which re-election happens and the amount of work that is required for re-election, and then parallelizing them so that if you have multiple primaries failing, you can, or do you parallelize them, or is that still happening in serial?
There's something called epoch value. We want
Yeah.
only one new decision to be taken per epoch value. So it's still
Okay.
serialized, but there is a order to it.
Tell me more about the non-performance, just latency side of benchmarking that you do to make sure that this is a healthy system.
We don't want users to have any problem while they're running at a scale, and as well as in the 0.1% of the scenario, the system shouldn't break. So
Mm.
the goal was not to have a system which just doesn't work when these events which happens regularly these days of easy failure, like one node going down, all of these kind of failure scenario should be well tested so that users can comfortably and confidently run Valkey. So the part of the project, what we did was we wanted to take Valkey, run it in a public cloud environment with different instance types, set it up with the workloads and environment which a user would run in. And then we took scenarios which are like single node failure, percentage of failure, 50% of node failure, and then observe the characteristics of the system. Um, Along with that, we're running heavy workloads which a user would run, right? So with all of this in place, we were running it in a AWS EC2 setup. We didn't use
Mhm.
any of the basically managed cloud. Rather, we ran it on a public cloud. So we had to set up some orchestration behind it to be able to do all these operations. And then we designed a chaos injection framework where we can say, go kill these many primaries, go make some network partition. So all of that was also created to be able to benchmark the system. And along with that, we're constantly monitoring the CPU utilization and the node failures, and we were able to keep track of if there is any spikes. And if there was a spike, we had built in a flame graph to be captured as part of the spike. And then we were collecting those data. And after the scenario was done in terms of testing, we went back into checking what went right, what went wrong, and this was like a 2-3 months of work across three people in my team. So I like to give credit to Sarthak and Songbin, who were like doing all this quite passionately, I would say.
Wow. And how do atomic slot migrations play into this in terms of like running these large clusters, if at all?
It would feel slightly orthogonal that slot migration is a like a management tool of moving data from one shard to another. But I
Mhm.
feel all of these comes together as a whole. If you support 2000 nodes cluster, but you don't give a reliable piece of infrastructure which can move data from one shard to another, then people won't be able to scale in and scale out easily. So I feel all of these are like different pieces of the same puzzle. And I felt like with 9.0, atomic slot migration was a key piece which a user needs to run a cluster comfortably, and the administrator do not need to take in the pain of moving one slot at a time, figuring out what goes right, what goes wrong. the slot migration piece which existed as of now was not so smooth to run a cluster. So I think people actually oversize their system to be able to handle the load comfortably. And with this atomic slot migration, people can now be more dynamic. They can scale out when they're expecting more traffic, and this feature would basically take care of moving this data from one shard to another quite reliably. So, so we have both the pieces now. One, we have tested it thoroughly, and also we have slot migration, which is kind of quite handy for operators.
I think from where I'm standing, in the early days of this dictionary level caching, we saw a lot of work on single node. But with the Valkey project, I see major investment in distributed systems aspect of the ecosystem. And that really helps with the robustness of the platform at scale. Slot migration, the optimizations on the cluster bus, the ability to pick primaries quicker with less contention. What are the other kind of things that come to mind in terms of just improving resilience?
I think the aspects which made Valkey successful is taking the burden out of the user and helping them run the system, and they
Mhm,
don't need to take care of much of things. So, like you mentioned, the distributed system aspect, prior to the in-memory data structure, so a client needs to be aware where the data goes, and the sharding of the system needs to be taken care of by the user. And
mhm.
it's still not so easy to do all of it. You need to be really smart. Rather, the sharding approach, which Valky does, is quite smooth, and the data gets split by itself. You don't need to be worried about maintainability of the system. Like if you want to scale out, you can scale out very easily. The replication system is also kind of neat that you have high availability of the system. That's also quite handy that the data loss is minimal. There is some durability guarantee, but we are looking at improving that as well.
Are you excited about this whole forkless replication, or is there a different approach that you're more excited for?
Forkless replication would be a very interesting investment, and there has been some groundwork being laid up for that as well. The biggest pain which people have is to over allocate memory to able to handle the background save which we have. And with the fork, you might need almost 50% additional memory capacity to be able to handle writes during the background save. So forkless application would be handy where there is a lot of memory constraints in terms of you're not able to provision more, and then forkless application comes in and you basically are able to use the entire memory available for data storage, and it does all of it quite smoothly. So that is most likely going to get introduced in 9.1 is what my understanding as of now.
Yeah, UMs are horrible for your cache hit rates or if you're relying on data. So if you don't allocate enough memory because, forking required additional memory, you can basically the system and lose all the data that you may have had. And it could be kind of a domino effect, right? Then the replica hits, it becomes the primary, and the primary can fail over and so forth. So I'm pretty excited about kind of optimizations there to minimize the odds of in those corner scenarios. When you built this very large benchmarking fleet, uh, I suspect a lot of the work had to do with just the coordinating all of those benchmarking nodes. How did you collect the telemetry? Did each node just write to CloudWatch, or what was kind of going on to generate that image that you had on your blog that showed 1 billion TPS being achieved?
It was slightly customized telemetry built by Songmin. He was basically pumping those metrics from the node using the CloudWatch agent and pushing it at a very granular rate. I think it was at a second. That helped us collecting those metrics and be assured that, okay, the failover operation went through in 15 seconds, 20 seconds, as well as the latency and the throughput.
I'm curious. I've seen a lot of numbers. I've generated some on single node performance. I'm curious, did you see generally consistent performance when your cluster size got to 2000 nodes? Interested in hearing about the latency, characteristics, also like load and balance characteristics when you ran at that scale.
we were expecting there will be some possible degradation when we are benchmarking 100 to 50, 500,000, 2,000 kind of clusters. However, the improvements and optimization to make it stable and linearly grow, there wasn't any visible increase in latency. It was still sub-milliseconds, and the CPU overhead doesn't grow a lot. It's like going from 1% to 2%
Wow.
of overhead.
And that
Yes,
includes all the gossip overhead, all the
yes,
re-elections, all of that. You're seeing like roughly 2% overhead. Okay.
yes. I don't think anyone runs their CPU at 100%. This is at 100% CPU utilization. We're able to run a huge fleet of clients to be able to generate traffic. But I would suggest people to run at 80% CPU utilization, and you won't bother about the 2% overhead in that case.
Yeah, I agree with you. I think the people that run their caching fleet at 100% utilization are mostly just doing benchmarking. Running very large fleet, you generally have a lot more room than the 2%. I think the key is how much does the 2% impact the tail latency and how do you isolate its impact? Like, so are there any major locks or pauses that happen in the ecosystem, or is this happening on the IO threads, or is this happening in a separate thread the way like memory allocation does, for instance?
Not at this point. It's still part of the main thread, but we improve where there was tail latency jumps. If there are so many nodes disconnected and you are trying to connect in a TLS setup, so
Mhm.
we were discovering that, okay, the TLS connection takes longer and it can't be doing this huge pause for the actual data serving flow. So we basically rate limited it, like don't do too many connections at one go, rather do it in batches so that the tail latency doesn't spike. We tried to figure out those scenarios where the tail latency was increasing and tried to address those as well.
Fantastic. I continue to be impressed by you, Hari, and the entire Valkey community. I consistently see new improvements in resilience, in performance, in scale. It's an inspirational project. Thank you for being a part of it. Thank you for giving shout out to all your team members, or so many of them as well. And thanks for coming on the podcast today.
I'd like to thank you as well. You have been a constant cheerleading for Valky, and that's really helpful and motivating for us to do great work. And like you see, always, it's a community effort, it's a team effort, I would say. And that's what the project stands for. So, looking forward to more in the future.